Welcome to this tutorial on botulism toxin. In this case you don't need to know a lot about botulism toxin, but it's a worthwhile exercise given what you have learnt so far to do a bit of an analysis of how it works and what the protein looks like. So I'll ask a few questions and you might like to pause the tutorial at various points and just take a moment to see if you can identify the various things I'm asking you to look at. So first of all, what I've put up on the screen here is a representation of the botulism toxin protein. So the toxin is a protein, and you could tell that how. So first of all, what is it about this particular diagram that gives away that we're looking at a protein? So how do you know? After you've worked out how you can work out this is a protein, what are the various structures or protein structures you can identify in this diagram? How many different kinds of the ones you learnt about earlier in the year could you identify? Try that now. Let's now have a look at how the botulism neurotoxin actually works. You've just studied synapses and how they're involved in transmitting an action potential from one nerve to the next. Now remember, I want you to put a number of ideas that you've learnt together here to see if you can make some sense of this process, because it's certainly not beyond you. So we're talking here about a neurotoxin. Now the word itself gives away what the action of the poison is likely to be. So it's a toxin that's going to act on a neuron or neurons in some way. Its effect is to cause paralysis. Now remember, paralysis is the inaction of muscles. It's the inability of muscles to contract. So when muscles can't contract, you are paralyzed. The muscles cannot move. So this particular neurotoxin leads to paralysis, the non-contraction of muscles. Now muscles contract when an action potential arrives at the muscle fibre from a neuron. So a neuron must synapse with a muscle fibre for it to be able to contract. So let's have a look at this diagram. Again, you might like to pause the tutorial or the video just for a few moments and have a really good look. This is a great exam practice as well, to be able to interpret a complex diagram and see if you can work out what's going on. Don't believe for a minute that it's beyond you, because it's not. So let's have a close look at it. On the left, over here, you're looking at the normal action at a synapse, normal transmitter release. This is a neurotransmitter, like acetylcholine. So let's have a look at what's happening and then see if you can make sense of what's going on over with the neurotoxin. So you've learnt by now that when an action potential arrives at the end of a neuron, so that's this area here, which is the synaptic knob, that calcium floods into the cells and causes vesicles containing acetylcholine to move towards the membrane, and then through a process of exocytosis dump the neurotransmitter into the synaptic cleft, where it diffuses across the extracellular fluid and binds to protein receptors on the next neuron, or the muscle in this case, and will cause a muscle contraction. Then the acetylcholine gets broken down and recycled. Now there's one additional aspect to this tutorial that we haven't studied, and it's not important in the bigger scheme of things, but it is important in understanding how botulinum neurotoxins work. So see if you can pick it up, see if you can work out what it is that's involved in this process that we haven't talked about. So pause the video for a moment and have a really good look at this diagram to see what additionally is there over what we've studied so far. So hopefully what you've picked up is the presence of these snare proteins, which I must say I've never heard of, but I think I can work out what their action is here. So snare proteins seem to be involved in the vesicles that contain the acetylcholine. And these snare proteins seem to have a role in drawing the vesicle towards the cell membrane. So allowing the vesicle to combine with the cell membrane to allow exocytosis. I suppose that's where the word snare comes from. It captures the cell membrane. So the snare proteins seem to be an essential link between the vesicles and their ability to arrive at the cell membrane so that the acetylcholine can be removed and can do its work. So let's now have a look at the action of botulinum neurotoxins over on this side. So again, pause the tutorial for a moment, have a really good look at the diagram and see if you can work out what's going on. So if you've had a good look at this, you might have picked up that it would seem that the botulinum neurotoxin, which is a protein itself, remember, cleaves, that means splits apart, the snare proteins. So it would seem to break the snare proteins up into smaller chunks. Now your general knowledge of biology would tell you that if the protein is chopped up into chunks, that it's going to be no longer functional. It's not going to be able to do its job. So if the botulinum neurotoxin cleaves or breaks up the snare proteins, what is it that can't happen? Well, based on what you've just had a look at over here, it would seem then that the vesicles that contain the acetylcholine will not be able to bind to the membrane. So these vesicles will not be able to reach the membrane and therefore will not be able to release their neurotransmitter into the synaptic cleft, and that means that no neurotransmitter will bind to the muscle proteins, the receptors, and so there'll be no muscle contraction. Hence paralysis. It would seem that the actual botulinum neurotoxin is absorbed into the cell via endocytosis. So here's the botulinum neurotoxin. It gets absorbed into the cell via endocytosis, and when it's in the cell, it then causes that cleaving of the snare proteins. So it would seem that the neurotoxins act to destroy a critical protein that's needed to get the vesicles containing acetylcholine to the membrane. And without that being able to happen, the acetylcholine cannot cause a muscle contraction, and therefore we end up with paralysis.